Hello everyone. Today I'm going to talk about lighting control by drawing shadows. So in particular, I'm going to talk about art paper, spotlight, shadow guided, relighting via diffusion, which we presented at 3DV 2026. And this is work I've done at Laval University during my PhD. So let's talk a little bit about the problem that we're trying to solve. So we're in the setting where we want to do object compositing. So we have a virtual object, such as this armchair on the left, and we want to insert it into a target background. For example, this background image in the center, and we want to get a realistic composite on the right, where we have realistic shading on the object and realistic shadows cast on the ground and on the scene. So this is an output from a previous method called zero comp. And basically there has been now this new trend of what we call diffusion renderers, which are diffusion models that are trained to replicate the outputs of an actual light path simulator, such as a 3D engine, basically. So how do these diffusion renderers work? So again, in particular, a method called zero comp. So we're going to start with the background image, and we will use off-the-shelf neural networks to estimate the geometry of the scene, as well as the material properties. So the depth, the normals, and the albedo. And for everything that's lighting related, we're going to integrate all of this in a map that we call shading, which is obtained simply by dividing the image by the albedo. Now, for the object, since we assume that we have access to the 3D virtual model of the object, we can simply use simple graphics shaders to obtain the depth, normal, and albedo of the object. And here you see the unknown part. This is the shading of the object. So since it's lighting related, we don't know what the shading should be. So we just leave it as unknown for now. And then what we do, as you can see on the bottom left, is that we basically alpha blended the 2D intrinsic maps from the object with the 2D intrinsics map of the background, and we get these composite images. And you can see that near the object in the shading map, let me just use the laser pointer, we also masked out a region around the object, since the object might cast shadows on the background. So this is lighting related. So we mask out a part of the shading map. And then we feed all of this to the diffusion renderer model, which is trained on many synthetic or real scenes. And it gives us a realistic render such as this one. So these methods are very cool, and this is just a little background on them. There has been two methods in 2024, 2025, doing that kind of diffusion rendering, even more actually. So there's Zero Comp, which I'm second author on, and RGBX by Adobe. So these methods give us very realistic results, but the problem is that they don't provide lighting control, which you would get, for example, if you use a 3D engine such as Blender. You can just move around the light easily. And sometimes you can use text to control the light, but it's not as precise. And the second issue is that if you wanted to actually add lighting control to these models, you would need a data set to train on that. But the problem is that these 2D intrinsic image data set that they're trained on don't contain this 3D light information. So we're stuck with a problem. How do we inject this precise light control, 3D light position, direction, size, intensity, and so on into this diffusion renderer model? So let's take a step back and think about what happens when we shine a light on an object in 3D. So the object should actually cast a shadow. Here we show it in white, but it should be black, of course. And now when we look only at the shadow, we can actually, in our brain, infer where the light came from. So now we have a 2D image of a shadow, and from that we have the light information. So our insight is to now, instead of injecting the lighting, we inject the 2D guiding shadow into the network. But again, how do we inject this information? And here the key point is that we don't have a data set with these guiding shadows. We want to do it in a training-free manner on existing diffusion renderers. So yeah, our insight is that we can inject actually the shadow without retraining. So the first step is that we do a very coarse shadow blending. So we just composited the object albedo with the guiding shadow and the background. And then since we have a diffusion process, we're gonna blend this shadow, this coarse composite shadow, with the noisy latence ZT on the left. We're gonna do this at every time step. And we feed that to the diffusion renderer. And at the end, we get the relit image. We don't change anything, so we also feed the intrinsics as before. That's the equation that we use for linearly alpha blending the shadow with the noisy latence. It's not very important, but you can find it in the paper also. So now let's just look at what kind of results we get when we do this shadow injection. So on the left, you have the input to the method, which is the guiding shadow. And on the right, you have the prediction by our method, Spotlight, which is, again, training free and applied to an existing diffusion renderer called ZeroComp. So we see that the shadow is now a little bit refined, a bit smoother, and the lighting on the object changes a little bit, but it has a very minimal effect on the lighting of the object. So we're not satisfied. We didn't have the same level of control as we would like in a 3D engine. So now our second idea is to amplify the local relighting, again in a training-free manner. So we're going to run two branches of our pipeline. So the positive branch will have the target shadow direction, and the negative branch will have the shadow but placed in the opposite direction. So you can do that, for example, by turning around the light source that was actually used to generate the shadow by 180 degree in azimuth. So again, we run those two branches. We get two predictions, VT pos and VT neg. And then we're going to do something a little bit like a classifier-free guidance, if you're familiar with it. So we basically do take a vector from the negative to the positive vector, and we're going to amplify it by a factor of gamma. Basically, we can adjust that. In practice, we set it to a gamma of 3. I didn't show it here, but we also find that we can control that to control the level of control on the relighting. And at the end, we decode and we get the final image. So let's see what it gives now that we have this local relighting amplification. Now we can see that when we move the shadow around, I'm going to use the laser pointer again. We can see that there's near the armrest, there's like self-shadowing that starts to happen when the shadow is on the left. So here we can see it just above. So there's much more control now. Yeah, we're much more satisfied with this. Again, all training free. So how do we evaluate this now? So the issue is that there wasn't a real existing data sets to evaluate and benchmark lighting control. So you need to have a virtual object that's inserted in a scene, and you need to have the light that moves around. And if you want to do that on furnitures, it's very hard to have the furniture in the scene and removed from the scene. So we actually created a synthetic data set where we have real background images and photorealistic virtual objects. So we use the Laval Indoor HDR dataset and Amazon Berkeley Objects dataset, and then we're going to take basically random pairs of them, try to fit the object in the mesh of the background image, and we reconstruct the mesh and we place lights in 9 different positions. So it's just a point light source that we move around to simulate user control. And we render the ground truth using Blender. So we can get our guiding shadows this way. For example, here we show 5 different shadow directions. So let's look at some qualitative results. Here we show the input guiding shadow, and this is our output, which looks pretty good with good control and realistic shadows. And if we look at a previous method called neural gaffer, we can see that it listens to the light direction. Here it's actually also conditioned on the lighting, and it was trained for lighting control, not training free. But it doesn't listen to the background image and the surrounding lighting cues. And this is another method called IC light. It changes quite a bit the color of the object. We did a user study on overall realism where we asked the users to choose the most realistic image. And we found that our method was the best, but very close to a baseline that we created called zero comp plus SD edit. So we also created a user study where we asked the users to click on the uh, the video where there's more control over the lighting. So this evaluates a second aspect, which is control, not realism, and we beat this baseline by a good margin. We also have quantitative metrics in the paper, of course. And another fun thing that we can do is that we can actually hand draw the shadows instead of using, for example, shadow mapping to obtain a coarse shadow. And we can see that the object is still relit reasonably well with this guiding shadow. And we can also use a different checkpoint of the diffusion renderer, which was trained on to support metallic objects, so to support more complex material properties. And we see some very nice results here as well. And here some early results on 2D object compositing. So here we don't have access to the 3D model of this dog on the left. So we estimate also the 2D intrinsic maps from the object. And then we can also estimate the shadows to cast on the object. All right, so that's it for my presentation. If you're interested, there's the QR code for our project page, and we have code and data available. Thank you.
Thank you very much, Frederick. There's one question in the Q&A widget here. I'll read it off. If anybody in the audience has other questions, feel free to either drop in the chat right now or put it into Q&A. But the question here from Jim F is, how robust is the method when the drawn shadow is physically inconsistent with the object geometry or scene lighting? Does the diffusion model correct it, follow it, or produce a plausible looking but physically wrong output?
Yeah, actually, we tested that. It does something reasonably well. I could show it, but the well, we have an example in the paper where we can see that there's basically a window that casts that's the dominant light source, and when we put the shadow in an incorrect user-defined direction, such as here on the left, we can see that the shadow does still appear in the desired light direction, but the model still does something reasonable to kind of harmonize that with the light that's cast from the window, the dominant window in the background. But yeah, if you feed the correct shadow, then you're gonna get stronger relighting results.